well, thanks for coming, guys. Any questions that you have for me? No? Homework's going okay? No? Questions?
I could probably work through it. I just not get the right answers.
Okay. All right. Well, I do have office hours this afternoon, so if you drop in with anything, let me know. So we'll start off then with now talking about shear in thin open sections and what the significance is of the shear center. And then, so lecture 19 is what we'll get through today, and then lecture 20 is kind of a more complicated example, which will be what I record and post for in lieu of class on Friday. So, yeah, so just as a reminder, no live lecture on Friday. I will instead post a lecture. All right, so as you know, for a straight beam with a rectangular cross-section, the shear results from the change in bending stress or moment that occurs along the beam. So what we're looking at here is, right, cross-section with positive moment applied on this segment of finite length delta x, and our shear stress results from essentially that change in moment along the cross-section. So on the other end you would have the M and the normal stress. And we calculate our shear stress as equal to VQ over B and IZ, where V is the shear force at the cross-section, Q is the first moment of area, and that's equal to A1 Y1 bar. And it's the first moment of the shaded area that's shown in the sketch here about the neutral axis. So we've gone over this before earlier in the class, but just as a refresher, the point at which you're calculating the shear stress is defined by this variable distance y1 from the neutral axis. The area that we use to define Q is measured from that point at which you're calculating the shear stress to the nearest free end. And so the area that is enclosed by that space is your A1, and then the Y1 bar is the distance from the neutral axis to the centroid of that area. B in our shear stress equation is defined as the width of the beam where shear stress is computed. And to be more general, if you have something other than a rectangular cross-section, it's the total width of the material. So you could have, right, a box shape, and it wouldn't be the total distance between the two edges because you have a hollow space in the middle. So it would just be whatever width has actual material associated with it. So if we consider a small piece, it's already kind of hard to tell, but there's a little green square along the side of our segment, and we blow it up. The stresses, the shear stresses acting on that segment would look like this, due to positive moment causing a downward shear on this face, resulting in a downward shear stress on the face of the square that is adjacent to our cross-section. And then the heads and tails match. So another occurrence of shear stress from bending if you have flanges of beam cross sections, such as this channel shape shown here, is horizontal shear stress. So in this case, for this channel section, we would have vertical shear stress along the vertical segment, and we would have horizontal shear stress occurring on the flanges, which are oriented horizontally. So in this situation, we use the same equation to calculate shear stress, except B is the flange thickness for the horizontal shear stress. So same Q, same shear stress, but here B is equal to the flange thickness. So that's noted on the diagram here. And when we calculate Q, the area that we're looking at now is measured from the free end horizontally in the Z direction. So it's the area between where the shear stress is equal to 0 and where the shear stress is computed. So in this instance then, we measure Z from that free end. So Z is a variable in calculating A1. Y1 bar is still the vertical distance in the y direction from the neutral axis to the centroid of that area. So as the point at which you're calculating shear stress varies along that horizontal segment, the area will change, but unlike a vertical segment, Y1 bar will remain the same. So now if we look at what that shear stress looks like on a segment, on a little piece taken on the horizontal segment there, it will look something like this. So these directions shown are the directions that apply to the top flange under positive bending. So this is directions of shear stress for top flange with positive bending. If we were to look at the vertical, a vertical segment, right, that would go back to what we had before, look something like this. And then on the bottom, if we were to take a segment from the bottom, then that would look, that would just have the opposite directions. Because the bottom would be in tension. Alright, so now we're going to define shear center. If the channel is supported as a cantilever, you would like to know where the load P, vertical load, should be applied on the cross section so that it only causes bending and does not cause the cross section to twist, so no torsion. So if the load is applied at this location within the cross section, then it will cause some twist, you can imagine. This is exaggerated, but the shape would deflect something like that. If it's placed at the center of the flange, then it will still twist, but not as dramatically. And then if the load is actually placed off the edge of the channel shape, this is actually where the shear center is located for channel shapes. And this is the location where load should be applied so that there's no twist and only bending. So the deflected shape would look something like that. And it's common in practice to see, for assemblies like this, rigid brackets installed to allow for load application at the shear center in order to avoid that twisting. So this location is the shear center. Also known as flexural center. And it is the point of application that eliminates torsion. So for solid cross sections, the shear center is usually at or near the centroid of the shape. But for open, thin-walled sections like this channel shape, oh yes, you have a question?
Are the diagrams with the red pen supposed to be a cross section?
Yes,
Oh, okay.
the channel, yeah, exactly. So for open, thin-walled sections like this channel, the shear center is usually off of the section in a lot of cases, and in any case, for any thin-walled sections, the location of the shear center is important and can be a really crucial consideration for design so that you avoid unwanted twisting. So that's especially true whenever the torsional rigidity is very small, which is often the case in these types of sections. Now, the exact location of the shear center is based on the distribution of the shear stress. Specifically, it's the point about which all of the, about which the moments from all of the forces, the shear forces in the cross-section sum to 0. So we'll look at how to find that in the example. At the shear forces in the cross section. So next we'll look at an example then to find the shear center of a rectangular center. So here we're given the neutral axis location. Of course it's symmetric about the horizontal axis, so that helps us in a lot of ways, which you'll see. And we're told that B, or the width, is equal to h over 2, so that's a little redundant to have it written here since it's shown on the diagram. And the thickness is much smaller than h. So the thickness is intended to be constant around the entire cross-section, so you have the same thickness at each segment. And because it's much smaller than the other dimensions, that means that we can neglect higher powers of t, and also we don't need to split hairs like t over 2 when we're calculating material property or geometric properties and stuff. So you'll see we'll just simplify that process a little bit when we go through it. So we can think of it as a very thin section like so, and just treat the thickness as a thickness property and not necessarily worry about how that affects the length of each segment. So we can calculate the moment of inertia about z. From the vertical segment we have th cubed over 12. And then from the two flanges, the two horizontal segments, since it's symmetric, we have each is h over 2 times t cubed over 12 plus h over 2 times t times h over 2 squared. So this is just your parallel axis theorem applied to the two horizontal segments. And again, you can see how I simplified this with h over 2 being your d squared, d being the distance from the neutral axis to the centroid of the element, the segment, right? So even though technically it would be h over 2 minus t over 2 squared, we're neglecting that because that's a higher power of t, and so on. So we end up with th cubed over 12 plus 1/4 th cubed. So we get 1/3 th cubed for our IZ. Now that we've calculated that, we can move on to individual segments to start finding the shear stress. So first we'll look at segment AB, the flange. So we're going to have horizontal shear because it's a horizontal segment with a thin wall. We know that the shear stress varies with the z coordinate. Because the A that we use to calculate Q varies with that z coordinate. So we're going to take z equals 0 at point A. And we also know that B is equal to T in our equation. So we have shear stress equals V times A1 over BIZ, which is going to be V times, in this case, our A1 will be Z times T. Sorry, I missed a term here because we're Q, so we still need the Y1 bar. So VA1 times Y1 bar for the Q. So then our Y1 bar is going to be H over 2. Since T is much smaller than H, we don't need to worry about subtracting that T over 2 there. Divided by T and IZ. So this is our A1, Y1 bar, and that's our B. And we'll note that T is much smaller than H. Neglect the minus T over 2 part. Alright, so then plugging in, or simplifying this a little bit, we have shear stress is equal to VHZ over 2IZ. So we can see that the shear stress varies linearly in horizontal sections. With Z. So now we can calculate the shear stress at points A and B. We know that at A it should end up being equal to 0, so we should confirm that. Alright, so at point A, since we took Z as being equal to 0 at A, Z is equal to 0. Plugging that into our shear stress equation gives us shear stress of 0, which makes sense. And at B, Z is equal to H over 2. So plugging that in, we get our shear stress is equal to VH squared over 4IZ. And we can calculate the shear force by integrating the shear stress over the area. So we'll call that FAB. That's equal to, since the thickness is constant, we can write that as the integral from 0 to H over 2 of tau times T dz. And then substituting our terms for tau and bringing the constants out front, we get VTH over 2I times the integral from 0 to H over 2 of Z dz. Evaluating the integral, we get VTH cubed over 16 IZ. So looking at our segment AB then, the force, FAB, would flow in this direction. I'll write it up here. That's FAB. And because it's symmetric about the neutral axis, that z-axis, we can say that everything on DE will be the same as AB, except that since the normal stress is in tension, the shear will be in the opposite direction. So basically, thanks to symmetry, we don't have to do this calculation twice, which is always nice. So now we just need to find the shear stress distribution on BD, the vertical segment. So here, our B is for a vertical segment, business as usual, defined as the width of the material. In this case, that happens to also be equal to T. So once again, we have B equal to T. And our shear stress is equal to, we've got our VQ over BIZ, which would be equal to V over I times, now our Q, because we're somewhere in the vertical segment, we have the area in the top flange to consider, as well as whatever area is included in the vertical segment to our point that we're, from our point that we're calculating shear stress for. So we have our A1 still and Y1 bar, and then we also have our A2 and Y2 bar for our total Q. So here you can think of A1 as being just the top part, and A2 as being the bottom part, and we're not going to worry about splitting hairs with the thickness at the corner. So we'll just take it as H over 2 as the length for each segment. And then divide that by T. So shear stress then is going to be V over I, and our area A1 is H over 2 times T, and Y1 bar is H over 2, and our area 2 is going to be a variable now because we have our variable Y defining the point at which that area ends. So it's going to be H over 2 minus Y times T. So that is our A2. And then our Y2 bar is going to be half of H over 2 minus Y divided by 2. So that's the full distance divided by 2 plus Y then. So that simplifies to 1/2 times H over 2 plus Y. So here we're looking for this value, y2 bar, right? And that's equal to, just filling in the gaps a little bit, h over 2 minus y divided by 2 plus y. Alright, and then, so that's our q, and we divide that by t. And that simplifies to, we have t's that cancel out here. We have a t in every term. So that simplifies to v over I times h squared over 4 plus 1/2 times the quantity h squared over 4 minus y squared. And so that further simplifies to v over 2I times 3/4 h squared minus y squared. So we can see that our shear stress is a function of y squared. Again, this is y is a variable y. So we can see that our shear stress is not linear over the vertical sections, unlike the horizontal elements. I just lost my train of thought for a second. What was I going to write here? Variable. So the distribution is not linear in non-horizontal members. And that's for vertical shear force, which is a typical situation. Okay, so we can check a few things, right? We already calculated the shear stress at B in the horizontal section, so that should be equal to the value that we get when we plug in our y distance to point B for this evaluation. So we're going to check shear stress at B. So for this vertical segment consideration, y is equal to h over 2. So our shear stress, if we plug that in, would be v over 2I times 3 over 4h squared minus h over 2 quantity squared, which is v over 2I times 3 over 4h squared minus h squared over 4, which is equal to vh squared over 4I. And that is, alright, so now we want to calculate the shear stress at the neutral axis. So, I don't think I labeled it. I'll call it, C. Put point C at the centroid, but same idea. We'll say shear stress at C. For that, we know that y is equal to 0. So the shear stress ends up being 3 over 8 VH squared over I. And we can expect that is the location of our maximum shear stress on this section. So then we don't need to calculate shear stress at D because of symmetry. We know it should be the same as the shear stress at B. And we can now find the shear force on BD. So we'll integrate along the entire length of the segment, so that's from negative h over 2 to positive h over 2 times the shear stress and thickness dy. And that's equal to Vt over 2Iz times the integral from negative h over 2 to positive h over 2, 3h squared over 4 minus y squared dy. Evaluating this integral, you end up with Vth cubed over 3I. And the shear force is in the same direction as the shear stress. So on the vertical segment, it's downward. That's why on the top flange, I drew it acting to the left. That's the same direction that the shear stress is acting based on this diagram here for the top flange. So that's how you can find the direction of the force. It just matches the direction of the shear stress. So, next we'll summarize all of those stress distributions and then find the shear center. So in summary, we had, I've got the forces noted here. The distribution, right, we had 0 at A, a linear distribution along AB, so straight line there. And then, right, we had shear stress at A 0, and we calculated our shear stress at B, and then at D, or on the other side of B is what I meant to say, same value. At C, we have an increase, and then at D, same magnitude as at B. So we have a parabolic distribution from B to D with our maximum shear stress at C. And then at E, we have 0. So now we want to find the location of the shear center. As the point about which there will be no twist if a load is applied. Kind of said that wrong. It's not the point about which there will be no twist. That doesn't really make sense. The point where there will be no twist. So we want to sum moments about that point and set that equal to 0 because that's the definition of the location of the shear stress. So we initially just assume a general position of the shear center. In this case, assume that it's off to the left of the segment. If we assumed that it was to the right, we would find out that we were wrong just by getting a negative value. So we have our forces already lined up here, and this is the sum of moments just from shear forces. each segment. And for vertical loading, it's safe to say that the shear center lies on the neutral axis, so we don't have to worry about the vertical position. Horizontal neutral axis, specifically. So we have 0, setting up our sum of moments, is equal to negative FBD times E plus FAB times H over 2 plus FDE times H over 2. Since FAB and FDE are equal to each other, we have E is equal to FAB over FBD times H, and then plugging in our values that we found for FAB and FBD, that is V times H cubed T over 16I, and VH cubed T over 3EI, not EI, just I, times H. So all these terms cancel, and we end up with E being equal to 3 over 16 times H. So that's how you locate the shear center. Yes, questions?
What's the first force?
What's the what?
The very first force in the equation after 0 is equal to?
Oh, negative F, that's supposed to be BD.
Oh, okay.
Yeah, sorry. Good catch. Any other questions? Just a little sloppy writing on my part. So if the force is horizontal, then you have, we'll just kind of quickly explore this. Considering the same channel, you have an applied force P, then the distribution of shear stress would be parabolic on the horizontal segments. So stress distribution would look something like this. And then on the vertical segment, it would actually be constant. And your forces would flow kind of like this for the P acting in that direction. And then if P was acting away from the channel, the direction of the shear stresses and forces would just reverse within the section. So your shear stress is linear in the web and nonlinear in the flanges. And then if you only have two segments, talking about the shear center now, the shear center is where they join. So if you have an angle, the shear center is located at the corner. And if you have a cross shape, the shear center is at that junction. A T shape, that junction as well. And that applies to any, you know, any orientation of these as well. So if you have something like that, the shear center at the junction, and the forces would flow typically heads to tails. On the T shape, it would flow left to right and then down. Then this is for vertical shear. So it looks something like that. If you have a T shape that's built up, right, or if you want to think about this in more detail, then the shear center is at the location where the pieces connect, so not necessarily at the center of that, not necessarily where the center lines intersect, but where the actual material intersects. And then if you have doubly symmetric sections, of course, it's located at the centroid. All right. Any questions? So, the example that I'm going to record for Friday is what's on the next few pages. So it's just a bit more of a complicated problem. You have some angled pieces to deal with, so I'm going to introduce how to address that. And then the homework problems associated with these lectures. I have them here. Here they are. Got problem 19.2, you can tackle this one now. Basically, got this horizontal, kind of eye shape, but have different flange lengths. And you want to find the shear center, basically. Where should P be applied to avoid twisting? So same thickness T in every segment. Vertical shear stress in the web, so this is the web, the horizontal piece, that can be assumed to be very small and neglected, so you just have vertical shear stress in the two vertical elements and horizontal shear stress in the web. And then again, you can ignore higher powers of T, so I think, let me double check. Yeah. You can ignore higher powers of T, like we did in the example. So you're given the textbook solution, so you can confirm your result, but you have to go through the process that we just went through in class to locate that shear center, to identify it in terms of the other geometric properties of the section. And then the other problem that I would wait until after viewing the example that I'm going to record, due to the inclined elements, just this open triangular section. So there's a slit at A, which means we treat it as a thin open section. And this one, you're going to find the location of the shear center in terms of H, and then find the once again, you can assume T is much smaller than H. So what is the centroid of the cross-section relative to the location of the shear center? So you're trying to find both of those items. And then also, just as a reminder, because it's symmetric about the neutral axis, right, you really only need to find the distribution of shear stress for two segments, A, B, and then B, C. And then it's just going to be mirrored over the neutral axis. So don't do a ton of extra work here. Make use of symmetry. All right? Sounds good. Well, let me know if you have any questions as you work through this. I will see you next week, and I will post the example by Friday. Thanks, everyone.